Hello class, we're about to start lesson 1-7, Attraction and Melted Chocolate. This starts on page 81. Our learning objectives is to write large and small numbers in scientific notation, to describe the significance of writing numbers in scientific notation, to study Newton's law of gravitation, and to compute the speed of light experimentally. Now we come down here to the bottom where we have, and we notice here that we have Newton's law of universal gravitation which describes the gravitational attraction between any two objects. This is the formula here, where F is the force of the gravitational attraction, M1 and M2 are the masses of the two objects, and R is the distance between the centers of the two objects. G is a number known as the gravitational constant. We'll see what that number is in a bit. So, we move on here to page 82, and we look here at problem number 1. It says, in Newton's law of universal gravitation, we were told that G is a constant. Look carefully at the equation that describes gravitational attraction. Describe the relationship between the gravitational force between two objects and the distance separating their centers. If the distance goes up, what happens to the force? What if the distance goes down? Okay, so first of all, the formula is from the previous page at the bottom, which is the force is equal to G times M sub 1 times M sub 2 all over R squared. Now, they ask us about the distance. Now, the R represents the distance according to the bottom of page 81, where the formula is located. So, this is just basically a fraction. So, if you look at this as a fraction, since the distance is in our denominator, that would mean if the distance goes up, force goes down. If the distance goes down, force goes up. And I'll give you a quick example just using some basic fractions. Like for instance, let's just say our numerator is 10. So if we make our denominator go up, let's say our denominator is 55. Our denominator is high at 55, but then we make it go low, which is 1. Now, which one of these will end up yielding the higher value? 10 over 1 is 10. 10 over 55 will give us a fraction of 2 over 11. So as the denominator gets smaller, the value gets larger. As the denominator gets larger, the total value gets smaller. So now, we look here at number 2. It says, repeat question 1, but this time describe the relationship between the gravitational force and the mass of the first object, M1. It might help to pretend that everything except F and M1 are just numbers. So we're still using the same formula. Now, a larger mass. Now we know, since the mass is in our numerator and this is multiplication, a larger mass results in a larger force. A smaller mass results in a smaller force. Okay, now we scroll on down here to problem number 3. Oh, let me give you all an example of this. So just like I did here with the numerators, kept them the same. We're talking about your numerator getting larger and what effect it would have on the overall result. So let's just say that our denominator is 5. Let's do two numbers. So let's make one of our numerators 1,000. And then we'll make our other numerator 1. 1,000 divided by 5 is 200. 1 divided by 5 is still just 1/5. Now, if you notice here, as our numerator got larger, our answer got larger. As our numerator got smaller, our answer got smaller. Okay, number 3. Why can you feel the gravitational attraction between you and the earth, but not between you and the person sitting next to you? Notice that I said gravitational attraction. Refer to the answer to question 2. Okay, now, and when they're talking about refer back to the question in question 2, it's dependent on the mass, because the person sitting next to you, you will have their mass. So it says a person is much smaller than a planet. So you can't feel the gravitational force. Okay, now number 4. It says, why can you feel the gravitational attraction between you and the earth, but not between you and Jupiter? Refer to your answer to question 1. And this deals with distance. Remember, Jupiter is too far away. So you cannot feel the gravitational force. Now, even though Jupiter is a bigger planet than Earth, we cannot feel the gravitational force because of its distance. So now, we move on here. Now, there is an explanation here at the bottom dealing with larger numbers. And so at the bottom here, dealing with these larger numbers, this is where scientific notation will come into play. So what we're going to do, you can read this at your leisure, but we're going to jump right into the scientific notation problems. So on page 83, it says write in large numbers in scientific notation. It says number 1, write a decimal point at the end of the number, then move it left so that there is just one digit before it. Number 2, multiply the result by 10 to some power. The power will be the number of places you move the decimal. And then we come down here using these rules. So now for questions 5 and 6, write each number in scientific notation. The number of people in the United States in November 2015 was 322,146,000. Okay, so now we want to rewrite this in scientific notation. Now, when you have a large number like this, and you don't see any decimal, or I should say any number, and you don't see any decimal, it's assumed that the decimal is at the end of the number. So our first step is to move this decimal until there's one non-zero number in front of the decimal. So this will give us 3.22146, and we don't have to write all of those zeros at the end. And then we will multiply this by 10, and depending on, we move to the left, so our exponent would be positive. If we were to move to the right, it would be negative. But we would count how many places we move. We move 1, 2, 3, 4, 5, 6, 7, 8 places. So it'd be to the 10 to the 8th. And this would be people. That would be our answer written in scientific notation. Now we come here to number 6. It says the distance in miles from Earth to the moon is 238,900. So we had 238,900. It's assumed to be a decimal at the end here. We will move it 1, 2, 3, 4, 5 places. So it'd be 2.389 times 10. And since we move 5 places to the left, the exponent would be 5. And this is miles. Now, it says we can also use scientific notation to write very small numbers using negative powers of 10, which is illustrated here. Now, the only difference between these two here is that you're going to be moving a decimal to the right and have a negative exponent, which is explained down here at the bottom of page 83. Now we go here to page 84. Go right here to the top. It says, in questions 7 and 8, write each number in scientific notation. The weight in grams of 1 grain of spruce pollen. We have it at 0 point, and we have 1, 2, 4 more zeros, and 7. Okay, now they want us to write this as scientific notation. So you have to move this decimal to the right till you get one non-zero number in front of the decimal. So you'll go 1, 2, 3, 4, 5. So it'll be 7.0. Typically, they would want you to write it as 7.0, or you could write it as 7 times 10, times 10, and then the power, we move 5 places to the right, it'll be to the negative 5 power. Okay, number 8. It says the average number of hours it took the U.S. government to spend $1 million in 2012. So it took 0.0021605. Now, actually up here, I should have wrote the word grams at the end of this scientific notation. Okay, now we're about to start problem number 8. Okay, so now we are converting this to scientific notation. So we need to move this decimal 1, 2, 3 places to the right. Because remember, we can only have one digit in front of the decimal that's not 0. So it'd be 2.1605 times 10. And if you notice, we move this decimal 3 places to the right. So it'll be to the negative 3 power. And then this would be dollars. Wait a minute. Oh, I'm sorry. No, hours. Because that's how long it took to spend $1 million. So that would be hours. So it'd be 2.1605 times 10 to the negative 3 hours. Now, if we look here at the next page on the back, it says write each number in decimal notation. Now, we just did scientific notation. Now, decimal notation is just the regular way we write numbers. So they want us to take this scientific notation and then make it into the regular way we write numbers. So this is what we would need to do. You have 9.085 times 10 to the 4th power. Now, by taking it to the positive 4th power, that means you would move this decimal 4 places to the right. So we would take 9.085 and move this decimal 1, 2, 3, 4 places. So your final answer would be 90,850. And this would be gallons or drops in a gallon. So it's 90,850 drops in a gallon. Okay, B. The mass of an average dust particle is 7.53 times 10 to the negative 10 grams. Okay, so we would take 7.53 times 10 to the negative 10th power. Now again, since this is negative, like this was positive, we move to the right. This is negative, that means we move to the left. So we have to move this decimal to the left 10 places. So we'll go 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And in all of these spots here, we will put zeros. So it'll be 0.0000 It'll be, should be 90753. So it'd be 0.00000000753 grams. All right. So that took care of problem number 9. Now we come down to problem number 10. It says when a number written in scientific notation has a positive exponent on 10, what can we say for sure about the number? The number is equal to or greater than 10. The number is equal to or greater than 10. 11. If a number between 0 and 1 is written in scientific notation, what can we say about the exponent on 10? Now, if you notice, if a number is between 0 and 1, that means that it's less than 1 but greater than 0. So it'll be some decimal or a traditional fraction. So that means that we will have a negative exponent. Okay, now we come here to number 12. It says fill in the blanks. If a number in scientific notation has a negative exponent on 10, to convert to decimal form, move the decimal place left because the number is less than 1. All right, now we go to this next page. Now this page here basically shows you what a scientific notation answer would look like in a TI calculator. Now some people still use the TI calculator, which is fine. So I am going to show this. But on the Desmos calculator, when it gives you an answer in scientific notation, it looks like scientific notation. So here, you have 7.44E3. Now, the 7.44 would stay 7.44. This E is times 10. This 3, the number behind the E, is the exponent. So this is what this means. All right, now we move on to the next page. And I believe this is the last page of this section here. Then we need to move on. All right, so it says a typical MP3 file fills about 4 times 10 to the 6 bytes of disk space. How many average songs can my iPod Classic, which has 80 gigabytes of disk space, hold? Each gigabyte is 1 times 10 to the 9th bytes. Okay, so now, if we have 80 gigabytes, we're going to multiply this because we want to change this into bytes. For every gigabyte, it tells us that it's 1 times 10 to the 9th bytes. And that tells us here. So we'll put this over 1. The gigabytes will simplify out. And this will end up being 80 times 10 to the 9th bytes. Now, they want to know how many songs we could get on this iPod. They tell us a typical MP3 file fills up this much space of disk space. So we would take our 80 times 10 to the 9th, and we're going to convert this to scientific notation. So we have a decimal here and move this one place to the left. So it'd be 8.0 times 10, And since we moved it one place to the left, we add 1 to this 9. So it'll be 10 to the 10th. And then we would divide it by this 4. We'll make it 4.0 times 10 to the 6th power. Now, if we divide this, we can do it by hand or we can put it in the calculator. I would suggest putting it in the calculator myself because I think it'll make it a lot easier. That's just my opinion, but but that's how I would do it. So we have 8 times 10 to the 10th power. Let me pull up this keyboard. 10 to the 10th power. That'll be in our numerator. Our denominator would be 4 times 10 to the 6th. And it gives us 20,000. So it'll be 20,000 songs. That's how much the old iPod Classic could hold. Okay, now 15. Use Newton's law of universal gravitation to find the gravitational force between the Earth and Sun. The gravitational constant G is 6.674 times 10 to the negative 11 power. The distance from the Earth to the Sun is 1.496 times 10 to the 11th meters. The mass of the Earth is 5.974 times 10 to the 24 kilograms. The mass of the Sun is 1.989 times 10 to the 30th kilograms. The units of force are the kilogram meter per second squared, also known as the Newton. So we would take our formula, that F is equal to G times M sub 1 times M sub 2 all over R squared. Now we're already told what these values are. The gravitational pull is this here, this 6.674 times 10 to the negative 11. Put that in a parenthesis. Times our numerator. We add the mass of the Earth is 5.974 times 10 to the 24th. And then we also have the mass of the Sun, which is 1.989 times 10 to the 30th power. Because remember, these m's are the mass. And then now we want to do the distance. The distance is given here, which is 1.496 times 10 to the 11th power, but that's squared. Now we can put all of this in our calculator, especially with us using Desmos. Wait a minute, let me back this up. Okay, so we have 5.974. Put that division sign in here. And then we would do times 10 to the 24th power. That arrow there. And then parenthesis 1.989 times 10 to the 30th power. Okay, now we need to do our denominator. We have 1.496. Let me put that in a parenthesis, because this has to be squared. 1.496 times 10 to the 11th power. Close that parenthesis, and then square the parenthesis. So now, if you notice here, our answer, hold on, let me make sure that I didn't leave anything out. Okay, put that in parentheses too. All right, 1.189 times 10 to the 30th power. 1.496 times 10 to the 11th squared. Okay, So our final answer for our force would be 5.3092944,823 times 10 to the 32nd power. And this would be newtons. Okay, so now we will go down here to the next problem. It says, Newton's second law of motion, F equals ma, m times a, where F is force, m is mass, and a is acceleration. For a situation where the force is caused by gravity, say when you drop a bowling ball off of a building, we can use the universal law of gravitation with a is equal to g times m sub 1 over r squared. Use the value of g, the mass of the earth, and the radius of the earth, 6.3781 times 10 to the 6 meters, to find the acceleration due to gravity near the Earth's surface. How does your answer compare to the value used in a typical physics course? A equals 9.8. For the record, the units for A are meters per second per second. Okay, so we had A is equal to G times M sub 1 over R squared. Now they told us what the gravitational force is in the previous problem. That was that 6.674 times 10 to the negative 11 power. Now we have to multiply this by this fraction. And then our numerator, we would need the mass of the Earth, which is 5.974 times 10 to the 24th power, all over. And then we have here the radius of the Earth, which is 6.3781 times 10 to the 6th power. And we would square this in our denominator. Okay, so now we'll put this in our calculator. So we have 6.674 times 10 to the negative 11 power. Now that multiplied by the 5.974. So I missed the 9 here. Do a division. Go back up to the top. And then it'll be times 10 to the 24th power. Then our denominator, we're going to put that in a parenthesis. It'll be 6.3781 times 10 to the 6th power. Then we will close the parenthesis and take it to the 2nd power. So it gives us, if we round this to, let me see, do they tell us a specific? Okay, if we round this to 1 decimal place, like they have here, it says, how does it compare? If we round it to 1 decimal place, it's the same. The same if we round to 1 decimal place. Okay, we're back. And again, it says if we round to 1 decimal place, the answer is the same if we round to 1 decimal place. So that turns out to be correct. So now, that's basically it for 1-7. Now we move on to 1-8. 1-8 starts on page 95. If 1-8 is called portion control. Now, our objective is to describe what apportionment is and why it's used. compute standard divisors and quotas, apportion items using a variety of methods. Okay, so if we go down here to the bottom, it tells us here in this bold-faced word, apportionment is the process of fairly assigning identical individual objects among individuals entitled to shares that may be unequal. We just pointed out that the most logical way to attack dividing up the seats in Congress would be to divide the entire population by the number of seats. This would tell us how many people on average would be represented by one congressperson. Now that's from an earlier example, but we're going to get to that in just a second. Okay, now the number is known as the standard divisor, and it plays a really important role in apportionment. So we'll highlight the formula next, but don't think about memorizing it. Think about what it means, and you'll have a much better chance of understanding this lesson. Okay, so now we're going to move on to page 96. You have the formula at the top here. It says the standard divisor for an apportionment process is the average number of people per seat. So we have standard divisor, total population, all over number of seats. Now it says a large city has 20 seats to be allocated proportionally among 5 districts according to the population of each district. The populations of the districts in thousands are shown in the table. So we have our table here. It says explain why it wouldn't be fair to just assign 4 representatives to each district. And what they mean by that is, since it's 20 seats, 5 districts, you could just do 20 divided by 5 and say, hey, all of them should get 4. But they're saying explain why that wouldn't be fair. And the reason why that wouldn't be fair is because their populations are vastly different. Because if you look at District 2 versus District 5, they have 4 times the population. So why should they get the same amount of representatives? That wouldn't make sense, or the same amount of seats. Okay, number 2. It says find the standard divisor for this apportionment and briefly describe what it means. Okay, so basically it goes like this. The standard divisor, according to this formula up top, the standard divisor is equal to the total population, and I'm abbreviating, divided by the number of seats. So the standard divisor, total population, now remember this is in thousands. It tells you here this is in thousands. So this is actually 240,000 divided by the number of seats. There are 20 seats. So that means that 12,000 is your standard divisor. So that means there should be 1 seat for every 12,000 people. Now number 3, it says notice that District 2 has exactly 1/3 of the population. It would seem perfectly reasonable then for the district to get 1/3 of the seats. Why won't District 2 get exactly 1/3 of the seats? And the reason being, and I will show this, you have to take 20 divided by 3, because this is the number of seats, and we said that they should get 1/3. But when you divide this out, this becomes 6 2/3. And the reason why why District 2 would not get 1/3 of the seats is because it does not divide evenly into 20. Because you cannot get 2/3 of a seat. All right. So now we go here to the back. And it says here, while we've seen that you can't assign seats simply based on what percentage of the total population a given district has, that percentage still plays an important role in apportionment. If we divide the population of a given district by the standard divisor, something interesting happens. Okay, so if you look here, we have this formula here. This right here is the same as the population of the district divided by the total population all over number of seats. I just rewrote it for a minute here. So when we come down here, we're doing the same exact thing here, but now we're going to change this to reflect multiplication. So population of district times, we know when we divide by a fraction, we take its reciprocal and then multiply. So it's the number of seats divided by the total population. It says now we can rearrange the multiplication a bit using properties of multiplying fractions. So we could do the population of the district over the total population times the number of seats. Now this is going to come in handy when we get down here to problem number 5. It says compare this to the line of reasoning in question 3. The fraction part of the above formula is exactly the percentage of a total population that lives in a given district in decimal form. With that in mind, perform the calculation in the formula above for District 3 in our example problem. Then write a description of what the result of the calculation tells you. So we're going to do the population of the district divided by the total population times the number of seats. And we'll put that over 1. So the population of the district would be 41,000, and we're doing District 3. Now, when they ask you to do District 3, they're not talking about up here. They're talking about on the previous page. District 3 is 41,000. Okay, now divided by the total population, which is 240,000. Now, since this is in thousands, you could have technically just put 41 over 240, but I just went on and wrote it all out. And then times 20. Now, when you put this in your calculator, we have 41,000 divided by 240,000. And then multiplied by 20. And we round that to 2 decimal places, so it's approximately 3.42. So what this is saying is they should get 3.42 seats if this was possible. But we know that's not possible because you can't get 0.42 of a seat. Now, we come here to the next page. It says the formula we built, which is the percentage of the total population that lives in a given district multiplied by the total number of seats, is the theoretical number of seats that each district would get if it were possible to hand out fractional portions of seat. We call the number the standard quota. Again, the standard quota is the population of district divided by the standard divisor. So now, for number 6, they want us to find the standard quota for each district in the city described on page 96. So I'm just going to write out these. This is District 1, be 32,000 over 12,000. District 2 would be 80,000 over 12,000. District 3 would be 41,000 over 12,000. District 4 67,000 over 12,000. And District 5 be 20,000 all over 12,000. All right, so we can go ahead. So 32,000 divided by 12,000 would give us approximately 2.67. The 80,000 divided by 12,000 will give us approximately 6.67. We already did District 3 back in problem number 5, which would give us 3.42. Then the 67,000 divided by 12,000 is 5.58. And then finally here, the 20,000 divided by 12,000 will be approximately 1.67. So these are all of the standard quotas. Now, we move on to the next page. It says, round each of the standard quotas you calculated in question 6 to the nearest whole number. Then add the results and explain why that won't work as the number of seats assigned to each district. Okay, so if we round all of these, if you look back here, 1 will be 3, this will be 7, 3, 6, and 2. So it'll be 3 plus 7 plus 3 plus 6 plus 2. And when you add all of those up, it will give you 21 seats. Now remember, we only have 20 seats that we could give. So we could put we only have 20 seats. That's why this does not work. So now, this has all been a build up to a few formulas that you need to familiarize yourself with. The first one is called the Hamilton method, and it was made by Alexander Hamilton. It says the methods of apportionment that we'll study are all based on first calculating the standard quota, then deciding whether to round up or down. For any district, the lower quota is the result of rounding the standard quota down to the next lower whole number. The upper quota is the result of rounding up to the next larger whole number. It says use your results from question 6 to fill in the table below for each district. Okay, now we already did the standard quota. The standard quota was right here on page 98. So all I'm doing right now for the standard quota is just copying these values in. So it'll be 2.67, 6.67 for District 2, 3.42 for District 3, 5.58 for District 4, and 1.67 for District 5. Now listen, I really don't like when they say to round down. So I'm going to give you an alternative to the definition for the lower quota. To get the lower quota, all you have to do is take the number in front of the decimal. The number in front of the decimal is the lower quota. Again, for the lower quota, it's the number in front of the decimal for your standard quota. So this is 2, 6, 3, 5, and 1. Now the upper quota, you just add 1 to your lower quota. So this would be 3, 7, 4, 6, and 2. Again, the upper quota, you just add 1 to your lower quota. And that gives you the upper quota. Okay, now we move on to page 100. It says here, use Hamilton's method to apportion the seats for the city described in the class portion of this lesson. In completing the table on the previous page, you've done most of the work already. Cool. Make sure you clearly write out how many seats each district gets. A table wouldn't be the worst idea ever. I took the liberty of drawing in my own table, but I'm going to rewrite what we wrote on the previous page. The standard quotas for these districts. Okay. Now the lower quota, is the number in front of the decimal. And the upper quota, we just add 1. Okay, so now we got all of that taken care of. Now, what we would do is this here. We add up the lower quota to see, this is how you would determine how many seats each district get. After you find all of this, you add up the lower quota. 2 and 6 is 8, plus 3 is 11, plus 5 is 16, plus 1 is 17. Okay, if this would have equaled 20, we would have been done. And these would have been the seats that each district would have gotten. But if you notice, we only have 17 seats here. But remember, we're trying to get up to 20 seats. So we could go off to the side and say 20 minus 17 is 3. So there's 3 seats left. So this is how you go about assigning those 3 seats. You will go back here to the standard quota. Look behind the decimal. Since it's 3 seats we're trying to get, we want to find the 3 largest values behind the decimal. Doesn't matter what's in front of the decimal, it's behind the decimal. So if you notice here, District 1 has 0.67, District 2 has 0.67, and District 5 have 0.67. 3 and 4 only has 42 and 58. So it's these 3. Now, let me tell you what happens to these 3. Okay, once you isolate the 3 here that you need, when you add these up, instead of using a lower quota, the ones that had the highest decimal, the highest values behind the decimal, you will use their upper quotas. So, for District 1, you will use the upper quota. District 2, you will use the upper quota. District 3, you would just use its lower quota. District 4, you will use its lower quota. And District 5, you will use its upper quota. So now when we add these up, 3 and 7 is 10, 13, 18. This will give us 20. Okay, now, that is the Hamilton method. Now we're going to move on next to the Jefferson method. Now, the Jefferson method is a little different than the Hamilton method. It says here, Jefferson method ends up being a trial and error process. We keep trying different divisors until the lower quotas add up to the right total. Let's give it a shot. Number 2, recall that the standard divisor calculated earlier was 12. Fill in the table below, in each case getting the modified quota from dividing a district's population by the modified divisor 11. So basically, since it's a modified divisor of 11, we're going to say that that's actually 11,000, not just 11. So when you take, as a matter of fact, I could write this down at the bottom. You have 32,000 divided by 11,000. That'll be District 1. District 2 will be 80,000 divided by 11,000. District 3, 41,000 divided by 11,000. District 4, 67,000 divided by 11,000. And District 5, 20,000 divided by 11,000. Now, let me explain to you why they went down. Remember when we just did in section 1.7, we said basically as your denominator goes down, your final answer will go up. So we needed more seats. So that is why our standard divisor was lowered from the 12,000 to 11,000 because we need larger numbers. So this would be 2.91, 7.27, 3.73, 6.09, and 1.82. Okay, now we need to put these values in. 2.91, 7.27, 3.73, 6.09, and 1.82. Now, they want us to do a modified lower quota. Modified lower quota, we still do it like a regular lower quota. We look at the number in front of the decimal. So that'll be 2, 7, 3, 6, and 1. Now it says add up the modified lower quota. Does the apportionment work? So we have 2 plus 7 plus 3 plus 6 plus 1. When we add all of this together, it equals 19. So it'll be no, still 1 seat short. Okay, so that took care of, well, we're not done yet. We actually have to do some more trial and error with this problem. All right, so with that being said, we come here to the top of the next page. Oh, okay, it says our next attempt will be to change the divisor we're using. Do you think we should make it bigger or smaller? Why? Now, we should make it smaller because we still need one additional seat. So it should be smaller because we need one additional seat. Now it says try again with modified divisor 10.5. Does the apportionment work now? Is it the same as the one we got from Hamilton's method? Now, I feel compelled to go back to number 4 for a second. I want to show you this. When I said that your denominator or your standard divisor or your divisor should be lower, that is because we wanted a larger number for our answer. But look here, let's say we just took 10 and we use them both as our numerator. And let's use a small number like 2 and a larger number like 5. 10 divided by 2 is 5. 10 divided by 5 is 2. If you notice, as your denominator gets smaller, your answer gets larger. Or you could say as your denominator gets larger, your answer gets smaller. That's why we need to get a smaller divisor. Now we come here. They want us to try this again with 10.5. Now 10.5 is really 10,500. So this is what we would do. We add 32,000 divided by 10,500. That'll be District 1. District 2 would be 80,000 divided by 10,500. District 3 and District 4. District 3 would be 41,000 divided by 10,500. District 4 would be 67,000 divided by 10,500. And District 5 would be 20,000 divided by 10,500. Now, when you put this in your calculator, this will give you 3.05. This will give you 7.62, 3.90, 6.38, and also 1.90. So we'll put these in here. 3.05, 7.62, 3.90, 6.38, and 1.90. Now that we have these values, we need a modified lower quota. So we'll take the digit in front of the decimal. Now, we need to add all of these values together. So we add 3 plus 7 plus 3 plus 6 plus 1, and that will give us 20. So we could say that it works. All right. Now, one other thing, there's one other question. It says, does the apportionment work now? It works. But it says, is it the same as the one we got from Hamilton's method? No. Two of the values in the districts are different. Okay, so even though we still had 20 seats from the Jefferson method and Hamilton method, they still gave us different values for what each district should get. For some of them, not all of them. Okay, now we move on here to 103. Now it says, we already know from question 7 in the class portion that using standard rounding rules won't work for the apportionment problem we've been studying that resulted in 21 seats. So we can skip right to step 2 in Webster's method. So we have too many seats. We should try a larger divisor. Okay, let's go back here to Webster's method. It says assign each district the number of seats by using standard rounding rules on the standard quota. Rounding up if the fractional part is 0.5 or greater, and down if the fractional part is less than 0.5. If the sum of the seats is equal to the number of seats available, use this as the apportionment. If not, modify the divisor and try again. Okay, so if we come here for problem, it says using a modified divisor 12.5, fill in the table below. Okay, so when we use 12.5, I actually didn't write this out, but let me write this out. We are 32,000 divided by 12,500. That's District 1. District 2 will be 80,000 divided by 12,500. District 3 will be 41,000 divided by 12,500. District 4 will be 67,000 divided by 12,500. And then District 5 would be 20,000 divided by 12,500. Okay, so now when we put this in our calculator, give us 2.56. Let me see, 6.40, 3.28, 5.36, and 1.60. So we're going to put these in for the modified quotas. 2.56, 6.40, 3.28, 5.36, and 1.60. Now, modified rounded quota, we'll just use regular rounding rules. So this will give us 3, 6, 3, 5, and 2. Now, when you add these up, that only give us 19. We still will be 1 seat short. So we're asked here, it says, so that means that we're going to have to use another modified divisor. Okay, so since 12,500 didn't work and we was 1 seat short, we may have to actually go with one more. And I would say let's just go down slightly to 12,250. So we had 32,000 divided by 12,250. 80,000 divided by 12,250. 41,000 divided by 12,250. District 4, we had 67,000 divided by 12,250. Then District 5, we had 20,000 divided by 12,250. So this would be 2.61, 6.53, 3.35, 5.47, and 1.63. Now, that's after we put that all in the calculator. So here I made a table. We had 32, 80 for the population, 41, 67, and 20. Okay. Now the modified quota, which we have down here, be 2.61. Then the next would be 6.53. Then for 3, it'll be 5.47. Oh, I'm sorry, 3.35, not 5.37. 3.35. And then 5.47 would go for District 4, and District 5 would be 1.63. So now we're going to do regular rounding rules. This would be 3, 7, 3, 5, and 2. Now when we add all of this up, this equals 20, and it works. It's a lot more work for this method and the Jefferson method, but it still works. Okay, now this last page for this section, they want us to tell whether or not these situations are that would they require apportionment or not. Now, if something can be evenly divided, it doesn't require apportionment. Apportionment is only used for things that cannot be evenly divided. Like you cannot evenly divide a computer or a whole person or something like that. So here, school district raises an extra $1.2 million with levy passes and decides to divide it among all of the schools in the system. So this is not apportionment. And then that's because a dollar can be divided up. Okay, number 9, a manufacturing company with 4 locations buys 22 new stamping machines. The plan is to divide them among the locations based on production levels over the last 4 years. This would be apportionment. A stamping machine cannot be divided up. Okay, next, number 10, it says each day a team of engineers that works for a utility company decides how to allocate power on the grid to various neighborhoods based on past usage statistics. This is not apportionment. And the reason being is power can be divided up. Okay, last but not least, each day, the manager of a large roofing company decides how to allocate workers to that day's jobs based on the size of the job and the time of completion. This is apportionment. A worker cannot be divided. You can't send half a worker to a site. Okay, now I will be sending you all videos for the 2-1 and 2-2. So they are broken up into parts, but I do have it separated on the email, so you all would be able to do 2-1 and 2-2. So please have all of your notes taken and ready, so you all can do your learning check assignments. Okay, are there any questions? Any questions? Okay. Well, I will be sending you the email within 5 to 10 minutes. So please make sure you look for it. And you all have been getting the emails I've sent you, correct?
Yep, I've gotten them.